signed areas of our oriented edges in our polygonal spline approximating y equals x squared. And so we can now finish our calculation. The signed area of the spline A0, A1 up to AN will be the sum of all these oriented edges and their signed areas. And so we're going to get 0 plus 1 plus 3 all the way up to the last one, which is going from AN minus 1 to AN, which is the nth one, n choose 2, or n minus 1 times n over 2. So when we add these things together, we add the various triangular numbers, then we get new numbers which turn out to be called pyramidal numbers. And the formula for this sum is n minus 1 times n plus 1 over 6. It's quite pleasant, sort of an analog of the triangular situation. Here we're multiplying consecutive numbers and dividing by 2, and here we're multiplying 3 consecutive numbers and dividing by 3 factorial, 2 times 3. The pyramidal numbers have this number in Sloan's encyclopedia, A000292. And we call pyramidal numbers because, for example, if you look at the case n equals 5, if you added up the first 5 here, you would get 1 plus 3 plus 6 is 10 plus 10 is 20. And that's what you get when you stack like cannonballs in a sort of pyramidal array with 10 on the base. And then above the 10, you stack 6, just exactly the spaces between those ones there. So space for 6 more to sit on top of that first layer. And then on top of that layer, you could put 3 more. And then on top of that 3, you put 1 more and get a nice stack of pyramids, of cannonballs, with 20 altogether. So 20 would be the case when you have n equals 5. There'd be a 6 here, which would cancel, and then there'd be a 5 times a 4. That'd be 20, so that's the 5th pyramidal number. Now notice that this expression could also be written a little bit more simply. Perhaps if we combine the n minus 1 and the n plus 1, we get n squared minus 1. So when we multiply by n, we get n cubed minus n over 6. And that's a cubic expression in n. That's telling us how the signed area of this OPS, this oriented polygonal spline, is growing as the number n increases. As n goes up, the signed area goes up essentially cubically. So it's roughly a polynomial in n of degree 3. And the lower terms are maybe not so significant when you're looking at large values. Now let's have a look at a related but different kind of application of these splines. To not approximate the curve over larger and larger regions, but actually to approximate the curve better and better over a fixed region. So let's look at y equals x squared just between 0 and 1. So it's some kind of arc of the parabola like this. And let's try to get at that arc by subdividing the interval 0, 1, let's say into 4 pieces. So from 0 we go to a quarter, a half, 3/4, and then 1. And we look at the corresponding points, still using our same parameterization. So here we're going to get 1/4 and then 1/4 squared, which is 1/16. Here we get 1/2 and 1/2 squared, which is a quarter. Here 3/4 and it's squared 9/16. And once we get up to 1, we'll get 1/1. Okay, so now we have these 5 points. That gives us a OPS, which is some kind of approximation to the actual curve over this interval. So let's have a look at the signed area of this associated spline, which is going to be, of course, the sum of the signed areas of its various oriented sides. So A0, A1, plus A1, A2, plus A2, A3, plus A3, A4, the sum of the signed areas of those 1, 2, 3, 4 different oriented edges. Okay, so we can calculate that because we have the coordinates of the points, and we just use our basic formula, AD minus BC over 2. So from A0 to A1, we're taking 0 times this plus minus 0 times this over 2. That's going to be 0. From here to here, it's 1/4 times 1/4 minus 1/16 times a half. There's there, over 2. From A2 to A3, go from here to here, it's 1/2 times 9/16, that's 9/32, minus 1/4 times 3/4, which is 3/16, all over 2. And the last one, you get 3/4 times 1 minus 9/16 times 1 all over 2. And you can check that these numbers turn out to be 1/64, 3/64, and 3/32, for a total of 10 over 64, or reduced 5 over 32. And what's that telling us? Well, that's the sum of all the signed areas. So that's the signed area made by this oriented triangle, and this one, and this one, and this one. So altogether, those oriented triangles just fill out this space that I've labeled with the green lines there. So we're getting the area that's determined by the spline and the starting point, which is a kind of polygonal approximation to a portion of the parabola, or an arc of the parabola, the part of the parabola between 0, 0 and 1, 1. It's an approximation to that. So that's a nice calculation, but now we can go further because we can generalize. Okay, so we're going to now stick with the same portion of the parabola, just from 0, 0 to 1, 1, and there it is there. And now we're going to consider a more general subdivision. We're going to now subdivide the interval 0, 1 into n different pieces, all separated by 1 over n. 1 over n, another 1 over n, another 1 over n. So n of these 1 over n pieces altogether. And then correspondingly, we're going to get these points on the parabola, where the parameter takes on the values 1 on n, 2 on n, and so on. So A0 will be 0, 0, then A1 will be 1 over n, comma, 1 over n squared. A2 will be 2 over n, 2 over n squared. So the y-coordinate always has to be the square of the x-coordinate. And then on k1, I'm showing you the kth one. So somewhere in here, a general kth one is k over n, and its square, k over n squared. And finally, keep on going until the very last one, when the k actually becomes n, and we just get 1 and 1 squared, so 1, 1. So we're going from 0, 0 to 1, 1, and all of these points are on the curve. They're equally separated along the x direction. And now, let's calculate the signed area of one of these oriented edges. Let's say the general one, from k minus 1 to k. So S of ak minus 1 ak. What is that? Well, there's the kth one. And the k minus first one is just like that, but there's a k minus 1 instead of a k. So if we take the formula, we have to take the k minus 1 over n, which is the first entry of that previous one, and multiply it by the second entry here, k over n squared. And then we have to subtract the second entry of the k minus 1 fellow, which is k minus 1 over n squared, times the first entry here, which is k over n. That's the AD minus BC applied to these 2 points. And we have to divide by 2. Okay, so what happens? Well, there's some common factors. There's an n and there's an n squared here. There's an n squared. There's n, so there's a common factor of n cubed in the denominator. In the numerator, we have a k minus 1 times a k as a common factor, and we get the same kind of thing as we did before. Here there's a k extra, and here there's a k minus 1 extra, so we get k minus 1 times k over 2n cubed. That's the value of the side area of one of these little oriented edges. So it's a lot like what we got in that first calculation, but now there's an n cubed also in the bottom. N is the number of intervals that we're assuming we've subdivided 0, 1 into. So in this calculation, the k is like an index that's sort of running from 1 to n. So k can be any value between 0, actually between 1 and n. And for any one of those values, we get a corresponding signed area of the corresponding oriented edge here. So now to find the signed area of the entire spline, we just have to add up all of these signed areas of the oriented edges. Okay, so the signed area of our OPS is the sum of the signed areas of its various oriented edges. And we can introduce summation notation. So this is our first go at some contact with that. We introduce this sigma sign, sum k equals 1 to n, to represent this sum. So instead of having to write it out this way, we just look at what is the typical term and what is the index that's running when it's changing. So we can express this in terms of the index k going from 1 to n. And then the typical term will be s of a sub k minus 1, a sub k. So this sort of compactly represents this sum. And this signed area is just what we computed on the previous page. That was k minus 1 times k over 2n cubed. So this is a compact notation for what's really this sum here. So this thing here is 0, and this first one is 1 over n cubed. That's the case when k was equal to 2. K is 2, we get 2 times 1 over 2, so that's just 1 over n cubed. This is the case when k is 3. We get 3 times 2 over 2, so that's 3. The next one will be k is 4. 4 times 3 over 2, so there'll be a 6 there, and so on. And the last one, when k takes the value n, will be n times n minus 1 over 2n cubed. So this is the thing written out in sort of traditional form. This is a compact representation of it. And with the compact representation, we can do things like pull out a common factor. So this n cubed is common to all of these terms. You can see that here as well. We can pull that n cubed out. And then what we have left is just a sum of the triangular numbers. 0, 1, 3, up to n minus 1 times n over 2. So notice summing k equals 1 to n of k minus 1 times k over 2. That was a triangular number. So we know, in fact, because we've just done it, what the sum of the triangular numbers is from k equals 1 to n. That was a pyramidal number. So we pull the n cubed out, and then we get the sum of the triangular numbers, and that's that thing there. And then we can simplify a little bit because one of these n's here can cancel. So we'll have n squared minus 1 in the numerator and 6n squared in the denominator. And then we pull out the 1 over 6, and then the n squared over n squared will be 1, and then minus 1 over n squared, so we can write it this way here. That's a very nice way of expressing it because it's making it clear now what happens to the signed area of this oriented spline as the number n of subdivisions gets bigger. As the number n of subdivision gets bigger, this quantity 1 over n squared starts getting smaller and smaller, getting closer and closer to 0. And so the total value here is necessarily getting closer and closer to 1/6. So as n gets big, this approaches 1/6. We've kind of done our first calculus computation here. Okay, great. What we've done is we said that, okay, we look at this part of the parabolic curve. We're going to approximate it with a linear spline, equally spaced with endpoints. We calculate the side area of that thing, get a very concrete expression for it. Then we look at what happens as the n gets big. We don't say those two things. We can just say, oh, it's getting big. As it gets big, we can all see that this is getting small, and this thing is getting closer to 1/6. Nothing mysterious about it. Now, that might motivate us to say, aha, that means that the area determined by the curve y equals x squared, and this segment is exactly 1/6. But we're not really in a position to say that because we have not yet defined what the area of this thing means. Okay? We're only computing the area of a polygonal spline at this stage, which we know exactly what that means. And we're talking about some kind of limit of that spline as n gets bigger. But we should not make the mistake to suppose that this is somehow calculating a priorly defined area of a parabolic arc. Okay, so let's just make a note of that. We do not yet have a definition of a parabolic arc. Nevertheless, when we do have such a definition, we certainly hope that the value in this particular case better be 1/6. And now I'm going to make another observation, very famous observation that goes back more than 2,000 years, to Archimedes. And it's this observation here, is that if you look at a triangle whose points are O, A, which is 1, 1, and this point B, which is 1/2, 1/4, halfway between our starting and end points, okay, that triangle there, its side area is easy to define. So if we're looking at the triangle OBA in this order here, then we have to take the cross product of 1/2, 1/4 with 1, 1. So that's 1/2 times 1 minus 1/4 times 1. That's a total of a quarter. We divide by 2, we get 1/8. Okay, so the area of this thing here, the side area of this triangle is 1/8. And we're making the observation that the 1/6, which is our guess as to the area of the parabolic arc, that is 4/3 the side area of a triangle. That's a true statement. this is 1/8, we can calculate that, and 1/8 times 4/3 is indeed 1/6. So there's a ratio between this parabolic area, the area of the parabolic arc, which we have not entirely defined yet, and this oriented triangle sine area, which we have defined, and the ratio is this factor 4/3. And that was remarkably discovered by Archimedes, but not just in this case, but actually in a much more general situation. So Archimedes, the greatest mind of antiquity, and possibly the greatest mind of all time, was really the first person to make a calculus computation involving a real curve, which is not linear. So Eudoxus before him had made calculus-type computations, and Archimedes made other ones as well, but they were often typically involving linear things like triangles and pyramids and such things. So this computation with the curve was really a brilliant thing, and we can call it Archimedes' parabolic area theorem. And so I'm going to frame it this way. So here is a parabola. Now, the ancient Greeks did not think about a parabola as being the graph y equals x squared in the Cartesian framework. They had a rather geometrical understanding of the parabola, and we'll talk about that in a later video. So let's just assume that we have this parabola of Archimedes. And Archimedes would have understood that one of the key things about this parabola is that it has an axis of symmetry. There's this axis right here, which is an axis of symmetry, so there's mirror symmetry here. Okay, so that means that's called a special direction. Okay, and here is his theorem. That if you take a parabolic arc, by that we mean, let's take 2 points on the parabola, say A and C, and let's consider the portion of the parabola between them. Okay, and so the parabolic arc that we're talking about is this region that's determined by this parabola itself between A and C, and the straight line joining A and C. So in this picture here, it's sort of denoted by the red lines. Okay, so Archimedes was interested in the area of this thing. So let's suppose that we have an idea of what the area means. His statement is that the area of a parabolic arc is 4/3 the area of the maximal triangle inscribed in it. What do you mean by that? So here's a triangle, A, B, C. And of all the triangles inscribed in this parabolic arc, so with 2 of its sides being AC, but B possibly being around here, this is the maximal one, the maximal area. And that's not too hard to see, but that's essentially due to the fact that here, exactly at this point here, the tangent to the parabola at this point is parallel to AC. Okay, so if you go down parallel here, you get to this point. That's sort of the maximal point. Any other point would be on this side of it, and so in terms of classical definition of area of a triangle, the height would be less. Height, when you think this is the base, would be less than it is for this value here. So this turns out to be the maximal triangle inscribed in this arc. And Archimedes is saying that the area of the parabolic arc is 4/3 the area of this triangle A, B, C. So denoting this here with this sort of symbol, the area of the parabolic arc, let's just introduce that temporarily, ABC, that's referring to this whole thing created by the parabola, is 4/3 the area of the triangle ABC. So Archimedes is going to talk about side areas and so on. So this is classical Greek mathematics in terms of standard kinds of areas. But nevertheless, it's really the first place where we get an inkling that we can get at the area of a curved region. Okay, this is hugely important for calculus. Here's this crazy curved region, well, not so crazy, but it's still curved. But Archimedes is telling us exactly what this area is. It's 4/3 the area of this triangle. Computation. So we computed what might be the area of this segment of the parabola from 0, 0 to 1, 1. So the first thing to do is to extend that to, say, from 0, 0 to a general point on the curve, say A prime, which is A comma A squared. And it turns out that we're able to do this, so really the same kind of argument, gives us a very similar formula for this area here, this area determined by the parabolic arc from 0, 0 to A squared. And it turns out to be A cubed over 6. So when A is 1, we get this 1/6, but in general, that's A cubed over 6. And that kind of syncs with our earlier computation of the dependence of such a spline area when the n gets big. Remember there was an n cubed kind of thing involved, so we're not surprised there's an A cubed there. Okay, so once we're in possession of such a formula, which we could get at by generalizing the argument that we just made, then we could look at a more general parabolic arc, say like this one. We have 2 points, A prime and C prime. So we were able to calculate this area, and similarly we'd be able to calculate this area, and then we can calculate the area of this triangle, because that's just a triangle. And so adding those 3 things, we'd be able to calculate the total area of that parabolic arc. And then we'd be able to compare that with the corresponding area of the maximal triangle contained in there, which is not going to be this one. It's going to be the one that you get by finding a tangent that's parallel to this one, or more simply, as the diagram on the previous page shows, another way of doing that would be to find the midpoint of the segment, wherever that is, and going down parallel to the axis. Go down parallel to the axis, you also find that maximal point for that triangle, as Archimedes understood. So there's a lot of interesting stuff here that we're going to want to do. We actually want to roll up our sleeves and make some computations. And that's the heart of calculus. What calculus is all about, is making computations. And so we're going to start doing that a little bit more, and we're going to now be focusing a little bit more in the direction of the work problems. So a lot of this development, I want you to read about it in the work problems, study that material, look at the diagrams carefully, follow the arguments. So the video is just a framework for this additional work that I'm going to be asking you to do, to look at, and then to do yourselves. So there's much to learn. I'm Noah Lauberger. Thanks for listening. I'm Norman Wahlberger, and welcome to the Algebraic Calculus. Today we're going to delve into one of the great mysteries and conundrums underlying the calculus. And it has to do with a very simple object, a circle. So it turns out that understanding the area of a circle is not only subtle, but actually logically problematic. And it's bedeviled people for literally thousands of years. So we want to talk a little bit about the historical background to this problem, and we'll see that Archimedes figures very prominently, just as he did for the parabola area computation. But I warn you that there's a big divergence here, especially at this point, between this course and pretty well any other course in calculus. And the reason is because we're treating this topic with the delicacy and the, say, skepticism that it really deserves. This is a hugely problematic issue, and we cannot skirt around that fact. Okay, so for at least 5,000 years, people have been struggling with the mystery of the circle and this determination of the area of a circle. Say the area of a circle of radius 1. So this is a question. What is the area of a circle of radius 1? Here's a circle. There's a center. There's a radius. We can assume we have some normalization. Got a ruler. That's 1 there. And we know how many squares of size 1 fit inside there. Well, people give this area a name. It's, of course, the Greek letter pi, so this represents the area. But the fact that we have area in quotes here is already alerting us to a potential problem, namely the difficulty in defining this in the first place. So in this course, we're going to give the following highly non-standard answer. Approximately, we can talk about an approximate area. But as for defining a precise area, I claim that that is not only difficult, it's actually impossible. It's something that will forever elude us. It's a goal that we can never attain. Even the definition. This is the crucial thing. It's not the computation. It's the definition of what this concept is. So when it comes to area, the circle, and we'll also see the hyperbola, are very different from the parabola. We get this fundamental divide right at the heart of calculus that students really need to be very familiar with. They need to understand that there's this big separation between what happens in the parabolic case and what happens in the circle or hyperbola case. So even from very early times, people have somehow been aware that this question of the area of a circle is something that's very hard to get one's hands on precisely, that there always seems to be some aspect of ambiguity or approximation involved. And this is a common theme throughout the history of mathematics, this exact problem, the determination of the area of a circle, even of radius 1. And we can go back to the Old Babylonian period, at least, around 1900 to 1600 BCE, that's the Old Babylonian period, and they had a formula for the approximate area of a circle, but it wasn't in terms of a radius. So they didn't think in terms of a circle having necessarily a radius. They thought rather in terms of a circumference. Like if you have a well, then you could perhaps measure around the well more easily than you could from the outside to a supposed sort of imaginary point in the center. So there's some practical reasons why circumference might be easier to deal with than radius. And in terms of the circumference c, their estimation was that the area of the circle was c squared over 12. It's a little exercise to show you that it's basically equivalent to having pi have a value of 3. In the contemporary Egyptian culture, we have the Ams or Rhind papyrus, one of our famous, one of the select few records of how the ancient Egyptians thought about mathematics. And this was created around 1650 BC, but it's very clear from the inscription that's actually a copy of earlier work that goes back a few hundred years earlier. And Ams refers to the scribe who actually made the copying. And this is problem 48 in that, no, it's actually problem 50 in the papyrus. It's a circular field has diameter 9 ket. What is its area? So here we have a circular field. In this case, the diameter is 9. So we can imagine it being in, say, a square box, and there's 9 in both directions. So here's the solution that's presented in the papyrus. Take away u 1/9 of it, namely 1. The remainder is 8. Make u the multiplication, 8 times 8. Becomes it 64, the amount of it. This is, in area, 64 setat. Setat being a unit of area. What I'm saying is that if the diameter is 9, you remove 1/9, you get 8. You square 8, you get an area of 64. So there's a formula here, which is not stated, but this is the formula, that the area is what you get. You start with the d, and you subtract 1/9 of d, you square it. That's then 64 over 81 d squared. And implicitly, this is using the value of pi, which is, as you can check, 256 over 81, which turns out to be 4/3 to the 4th. And that's approximately 3.16049. So that's not too bad an approximation to pi, which is usually 3.14159, etc. So that's quite an impressive, very early estimation of pi, okay? So we're putting pi in quotes because, from our point of view, pi is not part of our landscape, at least not as a number. We may think about it later on as some kind of approximate interval, which may grow or shrink depending on the circumstances. So there may be a more subtle interpretation of what pi is. But the idea of pi as being an exact number that you can put your finger on, forget it. That's not going to be part of our story. Just not part of our story. But nevertheless, we'll make touch with the historical basis. So whenever we talk about pi, we should have quotes around it. So imagine quotes around all these formulas pretty well. Okay, now another famous thing that happens is in Euclid, the book 12 actually of the Elements, it's 13 books altogether, so it's rather late in the piece. Proposition 2 talks about areas of circles and establishes another important ingredient in our understanding of circles. Euclid says, circles are to another as the squares on the diameters. Here's a circle. Here's a square on the diameter. Okay, so the diameter is that, and this is a square on the diameter. So move the diameter over there, then the square nicely contains the circle. Here's another circle. and a square on its diameter. What's this proposition saying? It's saying that the area of these two circles, their relation